So welcome to the afternoon session. So Shiv will be continuing his lecture on mapping class group. Shiv, over to you.
Thank you. Okay. So I will just recall the definition of mapping class group of a surface. Okay. So let us quickly recall. So again, S is surface of genus G with B boundary component and punctures. And then we have this orientation preserving homeomorphism group, right? S, which fix boundary pointwise. So then what is mapping class group? It is simply this group up to isotopy.
Excuse me?
Yes.
Would you mind if you switch on your video?
Okay, actually I have to connect to some other device for that. So, and there is some technical issue. I am not able to connect.
Okay.
So yeah, yesterday there was some problem.
So shall I try? Like, I don't know.
Yeah, you can try.
Okay, let me just try. So
Sharvesh, please pause the recording for a moment.
बाद में सर कट हो जाता है, मैं काट दूंगा.
Pause कीजिए, pause. Again recording. So Shiv will be continuing on mapping class group. So Shiv, please continue.
Yes. Okay. So I will quickly recall what is mapping class group of a surface. Okay. So let us start with S, surface of genus G, B boundary component, and N punctures. Okay. And this homeo plus S boundary S. So this denotes the group of orientation preserving homeomorphisms which fixes the boundary pointwise. So that is important. Okay. So it just doesn't like leave boundary invariant, but it fixes it pointwise. Okay. And then what is a mapping class group? You just quotient this by this equivalence where two elements are equivalent if they are isotopic. Okay. And so we fix a notation mod S for mapping class group. And here is a remark about punctures. So if your surface has punctures, right, so then you are allowed to permute them. Okay. So that we discussed already. And these were some of the examples discussed in the tutorial session, but I will simply just give you an overview, right? So for example, this is an order 3 element in genus 4 surface. And you can see this is a free rotation. So this is actually a restriction of a, like you embed your this S4 inside R3 and then you look at an automorphism of R3 and restrict it to this genus 4 surface. So this is a special kind of element. And why it is non-trivial? Because you can see the action like on these curves, right, is non-trivial. Okay. So then we also
you have mentioned for any genus G surface, you have order 3 element in mod is right. So
yes, order 3 element is there.
S5,
yes.
What will happen in case of S5?
Yes, very good. So okay, so that so how you realize it, right? That's what you were asking.
That is because here I have picture for S4.
So this is picture for okay. So the thing is, you may not always be able to realize it as a free rotation. Okay. So here you are able to realize it as a free rotation. So for example, you can ask, as you have asked, what about S5, right? Yes. Okay. So let me just okay. So let me just stop for a while. So actually, what happens? Like, for example, let me just draw S5 for a moment. So why it is counterintuitive is like 2, 3, 4. Yes. So essentially, you want to say that there is no like free rotation, right, of order 3 in S5. But here is the thing. So how you get it? So of course you need some more machinery, but the thing is you can start with the order 3 action on order 3 map on torus, right? So that we discussed, right, in one of the tutorial session that you look at this, right? Side pairing, yes, A, B, C, A, B, C. So you look at 1 click and you get, sorry, 2 click, right? So 2 pi by 3. So this is always there. So actually what it will do, like it will give you some kind of data associated with this like action, right? So this, let me just call it F. So this F acting upon S1, just torus, right? So this give you some kind of data. So let me just say what is that data. So that will be like, so these vertices are mapping to the vertices. So this is some, like, I cannot explain it right now, but it is, so you will get some data and there are some angles associated. So this data is something like, let me say 1, 2, 2, 3, right? Something 1, 6, right? Yes, I think that's correct. But let us not go into what is that data, but so there is some data associated with this. And then there is a way to compose these two actions, right? So for example, on torus, you have this C3 action, right? F here, then you have F here. So you somehow like, so there is this, okay, fixed point, right? In the center. So there is some local rotation. So you kind of combine these two. Okay. So there is a local rotation here. Okay. And you just combine it through it, just identify that by an homeomorphism, and you get a map on genus 2. So this will be give you a order 3 element on genus 2, and you continue like this. So you get the big picture, like how you get it. Yes. So this order 3 map will give you order 3 map on like torus with one boundary component. Yes. And you just glue it along this boundary. You get on genus 2 and you just continue this, right? Yes. So for example, so you have 2 such actions here, and then you just glue again. Okay. So that is ideal. But of course, this requires more like knowledge that we have not discussed so far. How you giving a combinatorial data, how you describe cyclic and any finite outer element. So that we have not discussed. But this is a rough way. Okay. So I hope I answered this, but we can discuss more about this in the tutorial session. If, like, okay. Actually, I can give you a map precise how you encode this information. So we can do that. Okay. So okay. So this also we discussed like this order 2 element, and this is very important element, hyperelliptic involution, and in a way it is also special that it comes from an automorphism of R3, right? So you are embedding your surface in R3, and then you are looking at. So this is in some sense special, right? Okay. So this we already discussed, and this is also we discussed, right? Order 6 element. Yes, on torus, right? And as we discussed in the beginning, this is a non-trivial element because you look at the action on the curves. Yes. So this is non-trivial, and this was an order 10 element in mapping class group of, right, to genus 2 surface. So this also we discussed. So this is a decagon with opposite side pairing, and quotient you can see by other characteristic argument that it is genus 2. Okay. So okay, so these were some examples. So today we will start with this very important result, which is known as Alexander trick. Okay. So what is this result? So if you look at the mapping class group of a closed disk, right? So that is a trivial, right? So there is no element other than identity in mapping class group of a closed disk. So this is very important result. So how you prove this? Okay. So let us identify closed disk with this set. Yes. Okay. And you start with any homeomorphism. Yes, which of course by convention, like we had, that it should fix boundary point wise. So what should be your claim? Claim should be phi should be isotopic to identity. Yes. Okay. So let me maybe draw another schematic picture that will help. So what is the idea? Idea is so suppose this is your disk, right? And then you have this boundary. Yes, boundary of the disk. So first thing is you stay there on the boundary, right? Initially you stay there, and then it is let's say F everywhere. So let me call it F inside. Yes. So then what you do is that you stay like, so So just enlarge this. So let me just. Yes. So this reason, right? So more and more time you like stay there. Okay. So you stay there, right? And you apply F inside this molar disk, and then just continue like this, right? So this F will shrink, and ultimately, right, your map is identity. So that is the Alexander trick, right? So I hope the idea is clear. Yes. So first you have just your map is identity on the boundary, and whole disk it is F. Yes. So then what you do, right? So you just look at this green portion, right? And you continuously what you do. So on this annular region, right? Small. So your map is identity, and rest of the place it is F. And then this green region will grow and grow, right? So right. So you just push it. Yes. Oh, so just push it. Yes. So yes. So your F will shrink, and ultimately everything is identity. Yes. Okay. So here is another picture which is from this textbook. So how you look at it? So let us look at this cylinder, right? D2 cross 01. Yes. So and define this isotopy, right? Explicitly. So what you do, right? So let us define it from this D2 cross this interval close on 0, 1 on the open, right, to D2 via this rule, right? So inside this disk, right? Yes. So disk of radius 1 minus t. So what is the rule? Rule is this: 1 minus t phi x upon 1 minus t, right? And you can see this lies inside D. Yes, by definition, because phi is a homeomorphism, and if t is between 0 and 1, 1 minus t is also between 0 and 1. So this modulus is less than 1. So this makes sense, right? And on remaining part, it remains x in this picture, right? So this green portion in this strip, it remains like identity. And so what you defined here, so f x at 1, you just define equal to x, right? And then one can clearly see, right? So at time t equal to 0, you are here, right? So your whole region is so f, right? So this is your f, and then your f is kind of shrinking, right? This at each level you can see. So here you can see at each level. So this your f is shrinking, and ultimately everything becomes identity. Yes. Okay. So is this clear to everyone? I hope there is no confusion, because this is very important argument. Yes.
So it should fix the point, the center point, right?
Which one?
The origin.
Yes. Yes.
So we're assuming that.
Which one? Where? So it starts. It starts from here, right? So it is f, right? Yes.
So it fixes the center of this disk. We have to assume that, right?
But there is no need to assume that even, right? Why you have to assume that?
Because of pasting lemma. So at time.
No, at time t equal to 0, all I need is like on the boundary it is identity. Yes. So rest everywhere it is like f, right? So it is f actually, right? On boundary it is identity. I don't need that actually, but that is happened because of right, Brow fixed point theorem. There is a fixed point, we know, right?
Okay.
And you can isotope and consider, but okay, that is not important here, not required in this argument. Yes.
Okay.
Okay. So a quick corollary of this is if you want to see what is mapping class group of a two sphere that is also trivial. Yes. So how one argue that? Argument is not very difficult. So let us start with an orientation preserving homeomorphism, right? And you take alpha to be some simple closed curve, right? But we know, right, S2 has no essential simple closed curves, right? Yes. So whatever curve you will take, right? So F alpha is always homotopic to alpha. Yes. So you can assume, right, F of alpha equal to alpha, right? Yes. So what does this do? This will split your S2 into two disks, right? So now you, on each portion, so you can just apply Alexander trick. Yes. So this will give that F is isotopic to identity. Yes. So this is very simple, just extension of Alexander trick. Right? I think that's okay.
F may send one disk to other disk. Is it?
Huh? Yes.
F may send one disk to the other disk. It won't happen because of.
No, that will change the orientation, right?
That
yes.
is, okay.
Yes. So that we are not considering, right?
Yes, yes.
So if you consider then you have to consider Z2, right? Like that will be the. Okay. So okay. So now we can start with the most fundamental elements in mapping class group, which are known as Dane twists. Okay. So. And you must have realized so far I am only able to give examples of finite order elements in the mapping class group, but we never talked about infinite order elements. So this was the reason that I have not introduced Dane twists, and we will see these for our examples of infinite order elements in mapping class group. So how one defines a Dane twist? Okay. So let alpha be a simple closed curve on S, okay, on a surface. So what you do, you take a annular neighborhood of alpha. Yes. So as you can see, yes, and you can parameterize it. Just identify it with annulus, right? S1 cross 0, 1. Yes. So then, first of all, I am defining what do you mean by Dane twist, right? As a homeomorphism, not as a element of mapping class group. So what is the meaning of Dane twist as a homeomorphism? Yes, and you can see there is a choice involved. Yes. So this is a map T alpha from S to S. So if X is not in this annular neighborhood, yes. So then what you define, you just define it to be identity, right? T alpha X equal to X. Yes. And otherwise, how you do? So you have parameterized this S1 cross 0, 1, let's say theta T. Okay. So if X is, let's say, E2 pi I theta T on this annulus, so what it does, it will rotate by just say T, right? So you just map E2 pi iota theta T to E2 pi iota theta plus T. Okay. So and you can see what will happen. So that is explained in this diagram. Yes. So you look at this curve, right? Or just let me say that this arc. So what happens to this arc which intersect alpha? Yes. So if you apply this twist, right, around alpha, so this will be right. So you can see, right. So what happens when let's say T equal to 0 and T equal to 1, right? At T equal to 0, what is it? It is 2 pi iota theta T, right? And what is T equal to 1? Complete round, right? 2 pi iota theta plus 1, right? So 2 pi iota theta plus 2 pi iota. So complete 2 pi term, right? So second diagram is more convincing, right? So you look at this annulus. So this is this green curve, right? And so you just make a full like twist here, right? So I'm twisting on the left, right here. Yes. So you just make a full twist, right? And just come back. Yes. So this is a twist in the annulus, and of course this is a local picture, and anything which does not intersect this curve alpha, right? So twist will have no effect on that. Yes. Okay. So here is another maybe picture for genus 2 surface. Okay. So just look at this picture. So here I am, and this is a picture from again the textbook. Okay. So just look at two curves A and B, right? So what is really a Dane twist? So first you cut. So suppose you want to describe Dane twist around A, right? And let's see what is its effect upon B. Okay. So you cut along A, yes. So then you just twist it, this part, right? This part you twist, right? So you will see what happens to this curve, right? This B. So when you twist, and then you just glue it back. Yes. So this is the effect of Dane twist around A on B. Yes. Okay. So here I am writing A. So there is a reason. So that has to be explained, right? So instead of alpha, I am writing A because now I am actually looking it as an element of mapping class group. Yes. Because you must have realized when we define Dane twist homeomorphism. Yes. So there are choices involved, right? So for example, I can take any parameterization, right? So there are uncountably many elements, right? So is this fine? So there are many choices involved, right? At each level. So if you look at this Dane twist homeomorphism, this is kind of not well defined, right? So there are uncountably many such elements. But if you look it as an element of mapping class group, then it is well defined. Yes, up to isotopy. So this element as an element, so this TA, right, as an element of mapping class group makes sense, right? And this is well defined. So that kind of transition is always there when you go from homeomorphism to mapping class group, right? And we will see eventually that mapping class group is finitely presented, so it is countable. So you have kind of coming from something uncountable to countable, right? So there it is evident. Yes. So is this action clear? Like, so what is a Dane twist? Because this is like most fundamental element for us, and it will be used many times. So if there is any confusion, you can ask. Yes. And there is a convention also. Okay. So what is a left Dane twist and a right Dane twist, right? For example, this is a left Dane twist. So you can take inverse of this, that will be right Dane twist. Yes. So, okay. So here are some maybe remarks. If geometric intersection number of A and B is 0, right? So then you can see, right, this action, right, TA on B is just B, right? It will not affect it, if, as you can see from the definition. Yes. And similarly, TB of A equal to A. So in order the action to be non-trivial, right? So there must be some intersection, right, of this curve. So non-trivial intersection, right, without bigons. Okay. So some intersection should be there. So only then you will get some non-trivial action, right? And of course, this TA on A is just A. Yes. Okay. Okay. So this next terminology is that of algebraic intersection number. We had not defined it earlier, but we will need it. Okay. So let us define. So let alpha and beta be two oriented simple closed curves in a surface. Right? So then the algebraic intersection number, right, denoted by I hat alpha beta, is defined as the sum of indices of the intersection points of alpha and beta, where an intersection point is of index 1 when the orientation of intersection agree with the orientation of S and -1 otherwise, right? Because there is an orientation of the surface, so you can choose one orientation, yes, and So for example, I can, okay, so let me just, so I can choose something like, so let me just draw it here. So for example, I can define something, let's say this, let's say this is A, B. So maybe I can define this to be +1, right? Yes. So let's say left to right. Yes. So you can just choose any orientation, right? And define your this notion of algebraic intersection number. So if you have a curve which intersects more, yes.
So if we reverse B, then it will be -1.
Yes, of course, yes. So if let me say I hat of BA, right, will be minus I hat of AB. Yes, right. So if you reverse it, of course, the orientation is so instead of B, just say you change the orientation, right? Like let's say minus B bar. Or
yeah.
So that will be minus. Yes.
So what is the role for the orientation of S here?
So you have to choose something, right? So there are two ways, right? You can orient, right? So you have to choose something. So it doesn't matter. So whatever basis for tangent space you choose, it will give you like for our this notion of algebraic intersection number. It depends upon the orientation. Right? So whatever you choose, for example, if I'm choosing this, right, to be +1, yes. So it will give you a consistent definition, right? But this definition, of course, depends upon the orientation. Yes? So you have to fix something always.
No, what if okay, you have two curves, alpha and beta, let's say.
Yes.
And I am giving some orientation for
yes.
alpha, for A and B. So the same way, if you fix, if the B crosses A from left, you put plus, and if B crosses A from right, then you put minus. Okay, so you go along the path A and come to the starting point. So and collect all plus and minus.
Yes.
So you sum them up.
Yes. So up to minus, just it will like it is like notion wise doesn't change. It depends upon orientation. That's it, yes. So up to minus, yes, there is a like.
Then where are you using the orientation of S?
So you have to fix something to begin with. For example, if I fix that this left, like going from left and right, suppose this is plus for me, like suppose this is the orientation I am fixing. Then accordingly you have a notion of algebraic intersection number. Yes.
Yes.
So it depends upon the orientation, of course. So if you changes that, then you have it like everything will change up to minus. That's it.
No, the point is, I am having with some surface SG or SG and B. So I am giving it two curve, just I said.
Yes.
So I am fixing an orientation for A and orientation for B. And I am saying when I go along A, and if there is an intersection, if the curves B crosses A from left to right, I am walking along A, let's say. Then I am putting plus, or if it is crossing from right, then I am putting minus.
Yes.
So by this I am collecting all plus and minus, and then I
so you are choosing different orientation other than just opposite to this, right? So you will get a so that's what here. So it depends upon orientation, notion. So but we will see when it comes to, for example, let's say action on the homology, right? So you define in both ways. So any way you define. So this, for example, if you look at the action of the mapping class group, in both ways, algebraic intersection number will be Prasad. Okay, and if you look at as an, for example, element of that I will discuss of the symplectic group, right? Still doesn't matter. So that will give you sp2z element.
So Rakesh, when you are saying that A passes B from left, there you're using the orientation of S.
Yes. Yes.
Left and right makes sense when you give orientation of the
surface.
Yes,
precisely. Yes.
Okay.
So you have to begin with something, right? There is choice involved, right? You fix something and you get a notion, right? So it is not independent of the orientation. Yes.
Okay.
Yes. Okay. So this I hat, so this you can regard it as a function from like this Cartesian product of first homology, right? That is just a binization of the fundamental group. Let's say first homology with integer coefficients, right, to Z. Okay. And so you know, right, this first homology with integer coefficients. So this is simply isomorphic to free abelian group of rank 2G. Yes. So you can choose a basis for this free abelian group of rank 2G, right? So let's so I am choosing this orientation, right? So for me, for example, here I mean this I of, let's say, AI bi equal to 1, okay, for let's say I equal to 1 to G. Yes. So suppose I choose my orientation like this. Yes. So I choose a basis. So this is a basis for homology, right? So now, so if you look at an element, let's say F of mapping class group, right? Of course, you have to choose some representative. So so then it has an action on like first homology. Yes. And so one can see this map, right? This action give you an element, right? So it preserves this form, right? And so let's see where this J comes from. Yes. So you have this basis, right? Ordered basis A1, B1, A2, B2, and AG, BG. Yes. So just look at the intersection. So intersection, algebraic intersection of A1 with A1. So you will get 0. Yes. So you look at algebraic intersection of A1 with B1, you get 1. Yes. And then you look at the algebraic intersection of, right, B1 with A1. So you will get -1, and you get algebraic intersection of B1 with B1, you get 0. So that's what this first block, and so on, right? So I hope you are familiar with this thing J. So this so J is this block matrix 2G cross 2G, right? And so you can represent this element of homology, right? Just look at its action on the generators. Yes. And so one can see this is represent an element of GL2ZZ such that it preserves this form, right? A transpose J equal to J. So why this happens? Because you know, right? If you look at an element, let's say A, so it should preserve, right, algebraic intersection number, right? So if you want to say algebraic intersection number between AI and let's say BI, right, this will be same as algebraic intersection number of AIB. Yes. So because of this relation, you will get this element, right? So this preserve this form J. So this is actually an element of symplectic group. Okay. So what is happening? So you are starting with an element of mapping class group. Look at its action on the integer homology, and it gives you an element of symplectic group. Yes. So this is called the symplectic representation. Okay. So for any like mapping class group element, you get an element in the symplectic group. Okay. And this is a group homomorphism. You can see. So this is give you a representation. Yes. Okay. And so this is an algebraic fact. So if you look at an element of sp2cz, then its determinant is always 1. So I think proof is not trivial. Proof is non-trivial, but it is a fact, right? That element of sp2z has determinant 1. So when you restrict to, for example, genus 1, right? So then it is simply SL2Z. Okay. So this we will use, and again, this is a fact that SL2Z is generated by elementary matrices, right? So this fact we will also use, that you can generate SL2Z by elementary matrices. Okay. So this form is clear to everyone, like how you get the symplectic representation, or if there is a confusion, like how you get, for example, this relation A transpose J equal to J, or why I have written this, right? So you can ask this.
No, my point, you have started with some element of mod SG, right?
Yes.
And then how are you relating with homology, or what? I didn't get that.
Okay, so if two elements of let's say two maps are homotopic, then they induce the same action on homology, right? This is a fact. So that's why. So it,
okay.
Or you are asking how you get this element H1 SG as a matrix?
At the end you are getting some map from mod SG to SP2 G, G, right?
Okay. So you, okay, let me just write it. So there is an element, right? So what is this? This is action on homology. Okay. So what is this psi of x? This is simply action on homology. Yes. So this is a map from Z2Z to itself, right? And that Z2Z, you can regard it as a like a vector space, right? But it is not a like field. But so it is a map from Z2Z to itself, right? And you can represent by that map by the matrix, right? Is there a problem? Right. Or I missed something.
Sir, you first, I did not understand. Sir, you get a matrix J by means I did not understand that. How did
okay,
you
so why you get this matrix? Okay, so
yes.
okay. So you have this form, right? This I had, right? And it is preserved, yes. Right? Yes.
Yes.
Yes. So that's why you get this J, right? This. Okay, so let me, how can I say this again?
Okay, so there are means 2G elements. So at ith jth position, you are seeing that that AI and some means if you are numbering them, then you are seeing
so there is an order.
So you are seeing their algebraic intersection number at ijth position.
So these are preserved, right? So that we know, right? Because it is so mapping class group will preserve the algebraic intersection number. Yes.
Yes, sir.
So you have to use that. And how you get this element of this element as a matrix? So that is simple, right? So this homology has a basis, right? So every element can be written as integer, like finite integer combinations of this 2G elements, right? A1, B1, and so on. Yes. So you look at its action, and you get another linear combination. And if you like this, you can always represent by matrix, isn't it? Okay. This is clear, right? So you just look at, for example, psi of f. If you have to see psi of f equivalence class, so you look at psi f equivalence class acting upon, let's say, A1, right? So just see where it goes. It is some integer combination. Just write it as first column of that matrix, right? Pick the coefficient. That's how you do, right? Write the matrix. What do you do? Yes. So it for every generator, right? A1, B1, and this is an order basis. So you get every column of the matrix. Yes.
So by action on homology, you mean the induced homomorphism? That is the terminology you're using?
Yes. Yeah. So right. Okay. So I hope this is clear right now. Okay. Yes. So now we will discuss.
Sir.
Yes.
Sir, in the proof of doing the mapping class group of S2, you have assumed that F alpha is isotopic to alpha. That's okay. After that line, you have assumed that F alpha is equals to alpha. So why could you assume such like
up to that? Isotopy now? So we have to prove up to isotopy, right?
No,
can't we
that's okay.
There is an so that we are using, yes.
That's okay, but how can we assume that F alpha is equals to alpha? F alpha is isotopic to alpha.
Yes. Right. No, that you are correct. So okay, so I can correct it. So that's fine. Yes. So that is up to isotopy only, I was. So if I have written equal, please remove it. Okay, equal I meant up to isotopic. Yes, because that's ultimately we want, right? So we can change f by isotopic such that, let's say, f of alpha equal to alpha.
So, can you please just go to that page?
Yes. Okay, okay, here it is. Yes.
Here it is. If alpha is
yes.
isotopic to assume alpha splits. That's my problem here, sir.
So I said f alpha is homotopy to alpha. Yes. So that one can. So whenever f alpha is homotopy to alpha, it means there is an annulus in between, right? So by you can change f by an isotopy and just assume f of alpha equal to alpha. That's what I'm saying. Okay.
No. My problem is to applying the Alexander trick here. One have the homeomorphism that fixes the boundary pointwise, right?
That's why we need it. Yes.
So what here you have taken f is the orientation preserving homeomorphism, but we need the homeomorphism to that fixes pointwise alpha, and after that we can apply the Alexander trick.
Right.
So what is
right?
That means we have to prove that there exists another homeomorphism which is isotopic to f and which fixes alpha pointwise. Then we can apply, na?
Yes. Right.
But how do you do that?
No, whenever you say f of alpha is homotopic to alpha, right? So it means there is an annulus, right? Between alpha and f alpha, right? So you can always change, like replace f up to isotopy, right? Such that you can, so f of alpha equal to alpha. Let's not call it alpha. You can name other curve in between, let's say core curve, right? So that is fine, right? So that can be done always. Yes.
Okay.
You got it, right?
Okay, sir, in the tutorial we can discuss this rigorously.
Sure. Okay. Okay. Yes. Okay. So let us see how you find the mapping class group of a torus, right? So we show that the symplectic representation, right, from mode T2 to SL2Z is an isomorphism. Okay. So that we will show. So we just saw, right? So you have the symplectic representation from and mode of SG to SP2Z, right? And for G equal to 1, SP is simply SL2Z. Right? Okay. So how will you do? So you start with the basis for the homology with integer coefficient. So let's say AB. So now I am kind of abusing the notation, right? So most of the time, like orientation was missing, right? So here, because of homology, I have to take oriented curves. So let's consider this as basis for first homology. Okay. So first thing, why this map is surjective? Okay. So that can be seen from, like, if that SL2Z is generated by these elementary matrices, right? 1 minus 1 0 1 and 1 0 1 1. That SL2 is generated by this. So if you can show that each of these elementary matrices has a pre-image, right, then you are done, right? Okay. So this can be easily seen that if you look at this Dane twist around A and Dane twist around B and see what is the image of this under psi, right, the symplectic representation. So you can recover both of these matrices. Yes. So this proves that every generator of SL2G, like these two generators, right, has a pre-image. So it means this map is surjective, right? Because image is generated. Right? Okay. So next thing you want to show is that this is injective, right? Okay. So I have given an illustration of action of this TB on this curve 1 1, for example. Here you can see, right? Okay. So if you look at this 1 1 curve here, right? So how this Dane twist around B will act? Yes. So this will give you a 1 2 curve, right? So this you can see. Okay, so let's see how this map is injective. So for injective, what you need to show, you start with the representative map, right, in the mapping class group of torus. So let's F be a homeomorphism such that, right, its symplectic image is trivial, right? So psi of equivalence class of F, right, in mode T2 is trivial. And so what you want to show? You want to show F is isotopic to identity. Okay. Okay. So first of all, this psi of this is trivial, and we know, right, this fundamental group of torus is simply Z plus G, right? This is abelian. So your F act at the level of fundamental group also trivially, right? So let us look at the universal cover, yes, of torus. Okay, so it is R2, and you have this canonical map, okay, covering map. So what one can do? So F acts trivially there, right? So you can lift your F, right, to a homeomorphism, right, linear homeomorphism, right, this F hat from R2 to R2, right, is such that F hat of 0 equal to 0. Yes, so because lift you can start from somewhere, right? That is a unique lift. So let's say it starts from 0. So here 0 I mean 0 0. Okay, and F hat is like this F tilde is Z2 invariant, right? So then so let us look at this homotopy, right, between F tilde and identity. Yes. So how we define it? So this is defined as R2 cross 0 1 to R2 by H of xt as T F tilde x plus 1 minus Tx. So you can see as T equal to 0, it is simply x, right? And at T equal to 1, it is F tilde x. Yes. So this is an homotopy between F tilde and identity map. So as F tilde is G2 invariant, so it will induce a homotopy, let's call it H tilde, from this R2 mod Z2 cross 0 1 to R2 mod Z2. Yes, and between F and identity. Yes. So we have proved that F is actually homotopic to identity, and we know homotopy and isotopy are same. So this equivalence class inside mapping class group is trivial. So psi is injective. Yes. So is this argument clear about how we prove it is surjective as well as injective? If something is not clear, please free to ask. Yes.
So why the images of those dendrites represent those matrices?
Why?
Like psi of TA is that matrix. Surjective.
Which thing you are asking?
Psi is surjective.
Yes. Okay. So this. Okay. So that you have to just look at what is the Dane twist, right? Around what is Dane twist of A and what is Dane twist of B. That's it. That's what you need to look at, right? So okay, should I draw a picture? So you can see, for example, at least TA acting upon A is A, right? So how you write A as 1 time A plus 0 time B, right? So that's what first element, at least you can see 1 0. And similarly here TB. So the second column you can see at least, right? So TB at B is B. So so B is 0 time A plus 1 time B. So that's why second column. At least this you can see. And now let us see how second column and this first column, right? So, okay. I need something big, right? Okay, AB. So let's see what is TB acting upon A. Yes. So what is TB acting upon A? Yes. Yes. That's what you get. Right? So this is simply A plus B in homology. Yes. So that will correspond to vector 1, 1. Okay. So I hope you can see the other part also. Yes. Yes. Is this clear?
Yes.
Yes. Okay. So this is a slightly non-trivial proposition. Okay. So next thing you want to see at least is like some properties of Dane twist, right? So we will see that Dane twists are infinite order elements. Okay. So first of all, let us see whether it is a non-trivial element, right? Though we have already seen in case of torus that it is a non-trivial, but in general, right? Let's say S is a closed-oriented surface of genus G. So in that setting, this always Dane twist around some simple closed curve is non-trivial or not. Okay. So let A be an isotopic class of a simple closed curve, let's say alpha. If alpha is not homotopic to a point or a puncture, then the Dane twist around A is a non-trivial element. Yes. Okay. So how you prove it? So you know, right? The action of what do you mean by non-trivial element? That it is not identity element. Right? An identity element has action on all simple closed curve, just trivial action, right? If you can produce that action of this TA on some curve is non-trivial, then you are done. Okay. So we will let's say sketch it in the case when alpha is non-separating. Okay. So suppose alpha is non-separating, then so this we have already seen that we can find a simple closed curve beta with intersection number of alpha and beta to be simply 1. Yes, so this you can always do in a surface. Okay. And you know what the picture is. Okay. So now let us denote B by an isotopic class of beta. Right? So then you can simply so you need a picture what actually happens. I have already drawn it for torus. You can just draw it for higher genus surface and see the intersection number of this TAB and B is simply 1. Yes. So this is easy to see, right? So the geometric intersection number of TAB and B equal to 1. So just realize TAB and B and see it, right, explicitly that you get no bigons and there is an intersection. So then TAB and B will be in minimal position and their intersection number will be 1, etc. So we have seen that intersection number of TAB and B is 1, right? So if TA is a trivial element, then you know what happened. Then TA of B should be B, right? Then intersection number of B should be 0. That is not the case. So TA is non-trivial. So similarly, you need to argue for a separating curve also, right? When alpha is separating. So okay, so that I have not done that argument for when alpha is separating, but there you need change of coordinate principle in same way. Okay. So if so let us skip that argument. But what happens if alpha is isotopic to, let's say, a boundary component, right? So how one argue that? So if alpha is isotopic to a boundary component, so you can simply consider a double of the surface, right? So that so you take a copy of S and just identify the boundary component, right? So then your alpha will become right, essential. Yes, and by this cases you will get the result. So yes.
Shiv. So regarding the first one,
yes,
that previous one, sorry, previous
yes.
theorem. So you are
Which
putting
one?
that mapping class group of torus is SL2 set.
Uh-huh.
Regarding this homotopy,
Yes.
so H, why it will give the homotopy H tilde?
Which one? Because F tilde is E2 invariant. That you have to use, right? Otherwise, it won't give. Why will it at least, for example, why will you can ask even it give a map from like, even a map, let's not talk about homotopy. Yes.
So what I was thinking, so H from R2 close interval 0, 1 to R2, and then you compose R2 with the quotient map, R2 to R2
yes, yes.
mod Z2.
Yes, yes. Okay,
so that will give you a map from R2 cross 0, 1 to R2 mod Z2. Okay. But I know F tilde is Z2 invariant, but even though why it will induce a map from.
Okay, so okay, so maybe let me just try to draw a diagram and see. Right? Okay. So let me just. So you have this R2 to R2, yes, and then you have this quotient map. Yes.
Correct. Yes.
So this we have, and let us call it
maybe R2 cross I2 R2. R2 cross.
Okay. Okay. So
homotopy you have, right?
Yes.
R2 cross,
right. So then this gives you map R2. Let's say R2 cross I2. Let's
R2.
say. So this I have. Let's say. So this will descend to like map from R2 cross this to yes. So, but I should not call it. Let me just call it pi cross identity. Yes.
Okay, pi cross identity. Correct.
Yes. Pi is this canonical projection. Yes.
Okay.
Okay. So let me call it H. And let us call it H bar. H tilde. Yes.
That's the thing I am saying.
Yes. Okay. So where is the problem? Let's see. Right. Let us write it. Maybe. What is H tilde of? Let's say.
Okay. H tilde of box X,
right?
comma T.
So let me just write it. So H tilde of, let's say, equivalence class, right, of X and let's say T, right? So what will be the definition? So this will be simply
pi of
pi cross identity, right? So this is simply H of, right? So here I will write pi of pi of X. No, wait.
Pi compose H, right?
Wait.
No. Pi compose H, right?
Wait. Pi. Wait. So pi composition as
pi compose H XT.
So this is
pi compose H.
Okay, so that is identity now. Okay, so this is the map, right? Pi composition H, H of this. Then you have to take the equivalence class also, right?
Sorry, I'm not getting.
XT equivalence class, right? Wait, is this fine? Let me see. So I just want to define it here, right? XT. So I know how to define this, right? H of XT I know, right?
No, so what I'm saying.
No, this is not.
No. Pi compose. No, just erase the H also. Now write pi.
So you want to say pi?
Basically, just the diagram is commuting. So.
No, that's true. Yes.
Pi compose H of XT. Yeah. So whether the diagram comes, that is the thing. So pi compose H of XT, right?
No, but you cannot write it pi, right? Okay, so I written pi. Okay, pi composition H. Okay.
H of
So yes. Right. Okay.
But so now the question is this H tilde well defined? That is the thing.
Which one?
H
this
tilde,
yes.
Why it is well defined? So what I am saying is that H of pi of H compose X plus vector, any vector comma T, it will be same as this thing, right? Vector means, I mean, some m comma n kind of thing.
Yes. So that is fine.
So the pi, it was a.
So actually, then we have to look at the definition of HXT, how we have defined, right?
You have just defined this line homotopy.
Yes, right.
Straight line homotopy, right?
Right.
So then F tilde is invariant, Z2 invariant, it is fine. But I'm worried about the second component, plus 1 minus T XC of it, right?
Okay. But why it is okay? So you are saying why it
hello, sir.
Like the lattice is going to lattice, right? There also, right? When you add,
hello,
that's
sir?
what you are worried. Yes,
that part. Yes.
Right. That you are worried. Okay. So that is fine. Right? It is kind of like, so suppose, okay, let me just take, okay, why, right? Yes. So if you consider the sum, right?
The point is that why this
yes
will induce a map H tilde from R to
sir.
Right.
Yes.
Hello.
Yes.
So can I say something about this?
Please quickly.
Sir, just you want to say that H tilde, how H tilde is well defined, right? So if I take, there are two images of a box of x, x1, x2, such that pi1 of x equals to pi of x1 equals to pi of x2 is equals to box of x, right? There's two pre-images. Well, so now H tilde of box of s comma t is equals to, we can write that I compose H of x1 of t first of all, okay? And since both are on the same image, okay, so by deck they are differed by deck transformations.
No. So maybe we can discuss.
We can maybe discuss in the tutorial. Yes, this is a good point. Okay. I thought it's simple. I ignored it that this other factor is there. Yes.
Okay.
No, this proof is correct. So only thing is we missed something, right? In the argument. So proof. There is no gap, I think, in the proof. As far as proof goes. Okay. Yes. So this is so next thing. This is a proposition from textbook, and I have skipped the proof of this. So, so let us look at this as a statement. It will be useful for us. So it describes how if you take powers of Dane twist and look at the intersection number, how it behaves. Okay. So let AB be two isotopic classes of simple closed curves, and K be any integer. So then, what is the intersection number of this? Let's say kth power of TA acting upon B with B. Okay. So this is okay. So I think I missed somewhere square. So this should be square. Yes. So this is mod K intersection number of AB whole square. Yes. So for proof, you can refer to the book. I am not supplying the details, but we will use this argument. To conclude, for example, that Dane twists have infinite order, right, and other results. So this we will be using. So you can see this at least for the case of k equal to 1, right? So what happens, right? And justify it. Okay. So let us just assume this for the time being, that this results hold, and try to see why Dane twists have infinite order. And so how one proof that Dane twists have infinite order? Yes. So you want to show that, like, right? So TAM is different from TAN, right? For all M, different from M. Yes. So, but if you see this expression, right, that is inherited in there, right? So why different powers of TA have different meaning? It represent different elements in the mapping class group. So this is clear from this formula, if you see, right? So because if you just change K, right? So you can start with some two curves A and B whose intersection number is positive. That is always possible, right? So, and whenever intersection number is like, let's say some non-zero quantity, let's say 1 or 2, whatever. So if you change K, right, the right-hand side here, right, it changes, right? So for different powers of K, you have like different action, right? This on B, that you can see from here. Because if action is same, then the intersection number will also agree. Yes. So this formula, right, is immediately communicate that different powers of TA, right, have different action, right? So on simple closed curves. So if action is different, it means different powers represent distinct elements in mapping class group. Right? So that is, if you look at the subgroup generated by Dane twist around a curve, simple closed curve, it will be isomorphic to C. Right? This is infinite cyclic group. So now we have at least infinite order element in the mapping class group. Yes. And earlier we were only able to see finite order elements. So now we have, and you will see these are these elements will actually generate the mapping class group. So these are very fundamental elements. So you can choose a finite collection of curves in the mapping class group such that taking Dane twist around those curves will generate it. Right? So that will come later on. Okay. So let us look at some properties of Dane twists. Right. So first is if so you look at the isotopy class of two curves, right? Let's say A and B, right? And suppose Dane twist agree, right? So this is if and only if like the classes agrees, right? So one way is easy, is if A equal to B, then Dane twists are equal. So so how you prove the other way around? So we will use that formula here. So let's assume A is different from B, and you wish to prove that Dane twist around A is different from Dane twist around B. Okay. So how one accomplish that? So for this, you can find isotopy class C such that intersection number of A with C is 0 and intersection number of B with C is non-zero. Yes. So this can be done always, right? It means like, so whenever you have, so let's say, so you can consider different cases here, right? So if there is a geometric intersection number between A and B, suppose it is non-zero, then you can take C to be right, equal to B. Yes. C to be equal to A, not B. So then you can take C to be equal to A, right? So then you have this condition, and in other case you have to use the change of coordinate principle to come up with this. Okay. So this is always possible. So given two distinct isotopy classes, you can find an isotopy class C such that intersection number of AC is 0 and intersection number of BC is non-zero. Right? So if this happens, so then you can see the action of TA and TB, right, is different on isotopy classes. Let's see how why action of TA and TB is different. So you just look at this calculation. What is the geometric intersection number of TA, C, and C, right? So this is simply like here K is 1, and by that formula it is simply intersection number of AC square. Yes, but A and C, their geometric intersection number is 0, so this gives you 0. But on the other hand, if you look at intersection number of TB, C, and C, right? So you get some non-trivial quantity, right? So this is 1 time intersection number of BC square, but BC intersects, right, non-trivially. So their geometric intersection number is non-zero. So the action should be different, right? So this geometric intersection number of TACC is different from geometric intersection number of TBC and C, right? Had TA and TB are equal, then you will get the equality here, right? Because we know, right, if two elements in the mapping class group are same, right, then this geometric intersection number is preserved. Right? There will be equality here, but we get this to be not equal. So TA must be different from T of B. Yes. So at least we know when we have distinct curves like up to isotopy, then we have distinct Dane twists, right? Okay. So we, for example, if you look at any surface of genus G, at least you can come up with distinct infinite order elements, right? So that information we have now. Okay. So next thing is what happens when you conjugate a Dane twist, right? So, and this is a very easy exercise you can do. So if you conjugate a Dane twist by a mapping class group element, right? So this is just like change of reference point kind of, right? So this is simply, so you can choose a curve, right, whose isotopic class is A, let's say alpha. So then what this T of F is, so it is just the Dane twist around F alpha, right? So if you conjugate, and this is easy to see by definition. So the way we define Dane twist, it's very easy. So this has an immediate corollary, like when an element of mapping class group commute with the Dane twist, right? So when it commutes, right? So you know, right? This is if and only if, right? FTA, right? F inverse equal to TA, and by previous exercise, you can immediately see this happens if F preserves it, right? F of A equals to A. So from this, you can compute the centralizer of a Dane twist, right? So if you want to say what is centralizer of Dane twist, it is precisely set of those mapping classes which preserve A, right? So that is like, let's write it. So if you want to look at the centralizer of Dane twist, right? So this is simply those elements which preserves them. Yes. So, okay. So next is if you look at isotopic classes A and B of two simple closed curves such that their geometric intersection number is 0, right? So then Dane twist around A and B commutes, right? And proof is easy. So suppose intersection number between A and B is 0. So then we know, right, by definition of Dane twist, that Dane twist TA, right, act upon B trivially, right? So by this previous exercise, right? So when you know, right, when F preserve A, right, F commutes with TA, right? So take F equal to TA here. Yes. So F action of TA on B is trivial, right? So this is just B. So TA commutes with TB, right? This corollary. Okay. So now you can look at the converse statement. So suppose TA commutes with TB. Yes. So this we know when this happens. So when TA preserves B, right, by the previous corollary. Yes. That was if and only if. Yes. So if TA B equal to B, then you can just look at intersection number of TA B with B, right? So it is simply TA B intersection number of B with itself, which is 0. But what is intersection number of TA B B? So this we know by the proposition that it is simply intersection number of AB square. Yes. So this gives intersection number of AB is 0. Okay. So this is the if and only if condition. Okay. So this is a immediate corollary. So if S is a, let's say, closed orientable surface of genus G, then the mapping class group contain a free abelian group of rank 3G minus 3. Yes. So this you can maybe. Okay, so I have given the explanation. So you can just simply look at the pan decomposition, right? Okay, so maybe let me draw a picture. So for example, you look at surface of, let's say, genus 2. Yes. So let's say S2, right? So here you can get these curves, right? Gamma 1, gamma 2, gamma 3, right? So let AI represent the isotopic class of gamma I, right? So then you can see, right, the geometric intersection number of gamma I, gamma j, right? This is 0. Right? So you can simply look at the group generated by T of AI, I equal to 1, 2, 3, right? So where what is AI? Where AI is isotopic class of gamma. Yes. So then you know, right, by the previous argument that TAI, right, and TAJ commutes, right, for every IJ. So if they commutes and each of it, this represent a infinite order element, right? So what you get, right? So you have a, so this is a presentation, right? T group generated by TA1, TA2, TA3, such that TA1, TA2, let's say TAI, TAJ is same as TAJ, TAI, right? So what is this thing? So this is isomorphic to, you know, right? Z plus C plus, right? Or you call it, let's say, Z3. So this you can do it for any genus surface, right? So you can always consider a pan decomposition, and so you know any pan decomposition will contain 3G minus 3 curves because of the Euler characteristic obstruction. So your surface will always, this mapping class group of a surface of genus G always contain a free billion group of rank 3G minus 3. Yes. So
how do we say that there aren't any other relations?
Which one? So where? Yes. So there. So sorry. Oh, sorry. So there are not any other relations. Yeah. So yes. So that requires. So because if AI, so if your gamma is a disjoint, right? Yes.
Yeah. Okay. Fine. Yeah.
Yes. So they commute, right? So do you require anything else then? Okay.
I want to ask one thing. So, hello, am I audible?
Yes. Yes. You are audible.
So, if the geometric intersection number is 0, then you have so many conclusions. So, if that is 1, then can you conclude something?
Yes. So there. So if that is 1, I think it is a free group with 2 generators. Right? That requires proof. I think ping pong lemma is used there.
No. For 1, it is a braid.
1 it is braid, or in free billion group, free group with 2 generators, isn't? Or 2.
For intersection, okay. 1 is a braid.
No, not for 2. 2. That is for 2.
For
yes.
2, more than 2 is a
2 and greater, right? I think for exactly 2 it is a free group with 2 generators. Yes. For 1 you have a greater.
Yes.
So for
so what is the conclusion? Can you just repeat?
So whenever geometric intersection number is 2, so we will I will see if I can prove that, not today.
Okay. I mean,
so if geometric intersection number is 2 or higher, for 2 I know precisely. For 2, by ping pong lemma, one can prove that the group generated by TA and TB is a free group with 2 generators. Okay. Yes.
And what about 1?
So 1, it is a like group with 1 relation, that is a braid relation. Right? So TA, TB, TA is same as like TB, TA, TB, right? Yes. So with this relation.
Okay, so from here, what I am saying, so from this picture, whatever you drawn over here, so I cannot get another TD for which, or TB, let's say.
Yes.
For which the geometry intersection number is 0 with the other 3, right?
Yeah, that's true. That's true.
That is why here you are
Right.
getting maximum, I mean, maximum abelian group is J3.
So this is maximum abelian group. Fine. Yes.
So my point is for other genus, so how to conclude this? There
so other genus also you have to just find a pan decomposition. That's it, right? Okay. So if you want, I can draw a picture for general case, right? Okay, so let me draw a picture for general case.
Sorry, I have one question.
Yes.
What the Rakesh is saying, like if you are not able to see any other curve which is not intersecting, that means disjoint. From there, how we can conclude this is a maximal subgroup, maximal abelian subgroup?
Which one?
Is it?
No, I cannot prove that. I know it is as a fact. No, you cannot prove it. Yes. Right?
Yeah.
That requires proof. I think that is a result of, okay, let me say, I forget the name. So big name is associated, someone like.
Okay.
Even I read the paper. So I in some other context. So that requires proof. That is not taken. Okay. So you cannot argue from just that there is a no pan decomposition like which contains more than 3G minus 3 curves, right? You cannot conclude from that. Right? So that requires argument.
Okay, so the maximal abelian group, I mean, for that you need some result, or you have?
No, you require proof, some other proof. So this argument will not work. Like just say, this is just give you an existence, but it does not this is not a complete argument that this is the maximal abelian group, right? This is a abelian group of maximal rank, 3 abelian group of maximal rank. So that is not concluded. Okay. So
maybe we can stop now.
Okay. Yes.
Take a break.
Yes.
And start at 4 o'clock.
Okay. So for tutorial, right?
Yeah, for the tutorial.
Okay. That's fine.
So could you show me the last statement, the pan decomposition? I want to read the statement once again. Yeah.
Okay. Where it is. So that's what I have not contained maximal because it is maximal, but so it contains a free abelian group of rank 3G minus 3. Yes.
Thank you, sir.
Okay. Okay. So I hope you can draw the pans, okay, or we can see that in tutorial.